Okay, in this video we're going to continue on studying the Newton's laws of motion. And we'll start off by considering a situation to ponder. Consider a heavy and a light person with the same size parachutes jumping together from the same altitude. Who do you think is going to hit the ground first? Or do you think they'll hit at the same time? Now, there are some different options here. You could say that the light person is going to hit the ground first, the heavy person is going to hit the ground first, they'll hit at the same time, or you might conclude there's simply not enough information in the problem to determine who's going to hit the ground first. But I think if you think about it, you might even be able to figure it out. Now let's keep in mind here that there are two forces acting on each person. There is the weight that's pulling them down, and then there's the air resistance that's pushing them up. The other thing to think about is each of them, when they leap off the plane and open their chutes, they're going to continue going downward faster and faster and faster until what happens? Until they reach their terminal velocity. Now, the question that you have to think about, is there a difference in the terminal velocity? Now, think about this and then try to answer it. Pause the video if you need to, but just really think about this for a minute and see if you can figure this one out. Okay, so the answer is that the heavy person is going to be the one that reaches the ground first. Because remember we talked about terminal velocity, and the terminal velocity occurs when the person's weight equals the force of the wind resistance or the air resistance. And so the skinnier person, the lighter weight person, is going to reach their terminal velocity faster, and so that means the heavier person is going to continue accelerating downward. Now we've been talking about force, but we haven't actually defined what a force is. So now we're going to have the definition of a force. And a force is simply a push or a pull. That's the definition. Whether it's you pushing against a wall, or you pulling on a rope, or the earth pulling on the moon, all of these pushes and pulls, they represent forces. And an interaction is something that occurs between one thing and another. And so, as an example, you can say when you push against a wall, you're interacting with that wall. Now, we've covered Newton's first law, the law of inertia, and we've covered Newton's second law, which tells us the acceleration of a body equals the force divided by the mass. Now we can look at Newton's third law of motion, the law of action and reaction. It says that whenever one object exerts a force on a second object, the second object exerts an equal and opposite reaction force on the first. So, as an example, if you press your hand against the wall has to press against you to keep you from crashing through the wall. And so the hand press and the wall press on each other with equal and opposite forces. We know that because our equilibrium condition says that the forces have to be balanced if the thing's not accelerated. And so the force of the wall pushing back against your hand has to equal the force of your hand pushing against the wall, otherwise there'd be an acceleration. Now, when you talk about Newton's third law of motion, we're generally talking about action and reaction forces. One force is called the action force, the other force is called the reaction force. They are co-pairs of a single interaction. Neither force exists without the other, and they are equal and opposite, equal in strength and opposite in direction. And now here's the last thing is the key. They always, always, always act on different objects. That's a very important idea. So let's do one of our quick little concept review questions. A soccer player kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of less than 1,500 newtons, 1,500 newtons, more than 1,500 newtons, or none of the above. Well, obviously it has to be one of those three choices, so it can't be none of the above. But what about the other options? Which one do you think it is? 1,500 newtons. So for every force, there's an equal and opposite reaction force. So if the foot kicks the ball has to have an equal and opposite reaction force against the foot. And so 1,500 newtons, the equal value, that's going to be the right answer. So in this figure, you can see some applications of this idea. If an object A exerts a force on object B, there's going to be a reaction force that object B exerts on object A. And here in this figure, you can see some different action and reaction pairs. The tire of a car pushes on the road. The reaction would be that the road pushes on the tire. A rocket pushes on gas. The reaction is that the gas pushes on the rocket. A man pulls on a spring. The spring pulls on the man. Action-reaction pair. The earth with gravity, the earth pulls on a ball that's dropped. Well, here's what's got to be true. The ball has to actually be pulling on the earth too. Now, remember that the acceleration is the force divided by the mass. If the mass is really big, that means the acceleration is going to be small. And so the mass of the earth is gigantically big, so it doesn't actually accelerate very much. But in principle, it's hard to imagine, but it actually has to accelerate upward a little bit towards the ball. That's what Newton's third law tells us. So again, let's do a review of these concepts. So here's our review question. When you step off of a curb and you're dropping off down below, the earth is pulling you downward. That's why you fall down off the curb. What is the reaction to this force? Is it a slight air resistance? Does it not exist in this case? Is it that you are actually pulling the earth upward? Or is it none of the above? And based on the last thing we talked about, I hope you recognize the answer is, you actually pull the earth upward. Because the earth is pulling on you, pulling you down. The reaction would be that you pull the earth up. Now here's another example of the third law of motion in action. When you shoot a gun or fire a cannon, the accelerations of the cannon and the cannonball are different. Why? Is it because the forces occur at different times? Or is it because while they may be the same theoretically, they don't work out to be the same in practice? Is it because the masses are different? Or is it because the ratios of force to mass are the same? Okay, so the answer is that this is because the masses are different. The accelerations of the cannon and cannonball are different because the masses are different. If we recall Newton's second law that tells us that A is equal to F over m, or the acceleration is the force divided by the mass, well, we know the forces have to be equal and opposite. They're action-reaction pairs. Newton's third law tells us that the force on the ball and the force on the cannon have to be equal and opposite. But what's different is that the cannon has a much greater mass than the cannonball. And so it recoils backwards, but it doesn't go backwards nearly as fast as the cannonball goes forward. Now, the acceleration of the cannonball is much bigger because the mass of the cannonball is much smaller. Now let's consider another situation. A high-speed bus collides head-on with an innocent insect. Some fly or something's just flying around, and the bus crashes into it. The force of impact splatters the unfortunate bug over the windshield of the bus. Now, what's going to receive a bigger force? The bug, or so will the bug get a bigger force, or will the bus get a bigger force? Do you think the bug receives the bigger force? The bus receives the bigger force? That they're the same force, or you can't say? So the answer is obviously they get the same force. Why is that obvious? Because we know Newton's third law. Newton's third law says for every force there is an equal and opposite reaction force. Now, why do a lot of people get this wrong? A lot of people that haven't had a course in physics or physical science want to say the bug, because the bug gets splattered. But what's actually going on is that the mass of the bug is so much smaller than the mass of the bus, it gets a massive acceleration. And that massive acceleration is what kills it. The accelerations are what are different, but the forces are both the same. Now here's another conceptual test of this idea. Imagine you've got two people of equal mass on a slippery ice and they push off from each other. Will they both move in the same speed and in opposite directions? The answer is yes. we know that they're going to be the same speed because it has to be equal forces, equal and opposite forces. And so that also tells us why the directions have to be opposite as well. It's again just a consequence of Newton's third law of motion. Okay, now there is one thing that can be a little bit confusing about this idea, and I wanted to go over it. And so we have this idea here, we have this single enclosed orange, and there is an applied external force that's causing the orange to accelerate. We know Newton's second law. If you apply a net force, there's going to be an acceleration. And here we're not showing an action-reaction pair because we only have that force acting on the orange. We don't know what the orange is pulling back on. Now let's consider the situation where we can see what's actually pulling the orange. The orange is being pulled by an apple, his buddy, and we can say that the action and reaction don't cancel. They don't cancel out. Why? Because they act on different things. Remember we said that Newton's third law forces act on different things. So, this force, the force that the apple is pulling on the orange, what's it acting on? It's acting on the orange. And that force, the reaction force that the orange is pulling back on the apple with, what's it acting on? It's acting on the apple. So they're obviously, these two forces are equal and opposite, but they're acting on different things. And so here's the main idea. This guy here, this force, is not acting on the orange. That's why these two forces don't cancel. But here's where it gets tricky. Now let's consider a system, we're not just considering the orange by itself anymore, but we're considering a system that has both the orange and the apple acting together. The apple is no longer external to the system. So the force pair is what's called an internal force or an internal force pair, and that does not cause an acceleration. So the action and reaction within the system do cancel. There's no external forces, that means there's no acceleration in the system. Now I know this might be a little bit confusing, but just bear with me because what we're doing is we're putting all the pieces together to fully understand this system. So we're going to look at the same system again, but now we're going to add another force into the mix. We're going to consider friction. And so that same internal action and reaction forces exist between the orange and the apple, but a second pair of action and reaction forces also exist, and that's going to be between the apple's feet and the floor. Okay, so what we have here is we have on the apple two forces. We have this force here, which is the force that the orange is pulling back with, and then we have the force of the apple pushing off against the ground. And that's really the reaction to the friction. The friction is pushing against the apple. So what we have is that the external friction force of the floor pushes on the system, which causes it to accelerate. A second pair of action and reaction forces do not cancel. So those two forces are the force of the foot on the ground and the force of the ground on the foot via friction, pushing off. Now here's another review question. Consider a helicopter, its rotors are spinning and it's providing lift. If the lift equals the weight of the helicopter, what does the helicopter do? Does it climb up, climb down, hover in midair, or none of the above? And the answer is it's going to hover in midair because the situation is a situation of equilibrium. The lift force equals the weight force, and so that tells you that the acceleration is going to be zero because they're in balance. Now here we have the same situation, but in this case the lift provided by the helicopter is greater. In that case, what does the helicopter do? Go up, go down, hover? What do you think? Hopefully you guessed that it climbs up, because that's what it does. If the lift force is greater, that means there's an unbalanced force pushing upward, and that's going to make the helicopter climb. All right, so we're going to continue reviewing Newton's third law, and here's a question: how does a bird fly? And specifically, how does a bird fly in the context of Newton's third law? Now you could say by flapping its wings, by pushing air down so that the air pushes it upward, by hovering in midair, or by inhaling and exhaling air. The answer is by pushing air down, because when the wings of the bird push the air down, the air pushes back on the wings and create lift and push the bird upward. One more review question here. So if you have an airplane, generally the wings are curved in a way to create lift, but they're also tilted. And their slightly tilted wings of the airplane deflect oncoming air downward to produce lift, oncoming air upward to produce lift, both of these or neither of these. And again, the answer is going to be oncoming air has to be directed downward. The wings push the air down. That means the air create a reaction force pushing the plane or the wings of the plane up, and that creates the lift. Now this is the last question on this idea. Compared with a lightweight glider, a heavier glider would have to push air downward with a greater force, downward with the same force, downward with less force, or none of the above. And the answer is that it would have to push the air downward with a greater force. Because it's heavier, it needs a greater force to lift it up. And so the forces would have to be equal and opposite, and that's why the answer is downward with a greater force. And that is the end of this video, so you can now proceed with the rest of the module.